Hello everyone, my name is Christian Steinmetz and I'm a PhD student at the Center for Digital Music at Queen Mary University of London. Today I'm going to talk about our paper, Filtered Noise Shaping for Time Domain Rules Response Estimation from Reverberant Speech. This was work at Facebook Rowdy Labs during an internship where I worked with Paul and Vamsi. So the room impulse response has many applications across signal processing, for example, informing reverberation and automatic speech recognition, for room acoustics analysis, or for creating virtual sound sources in VR and AR. Unfortunately, though, measuring the room impulse response of real rooms can be very challenging. For example, the kind of classical approach of creating a room impulse response from a real room would be to first take an intrusive signal, like a sinusoidal sweep, and then play this over a loudspeaker within the room. This generates a number of reflections, which can then be recorded by a microphone and post-processed with some DSP to generate an estimate of the room impulse response, which we can later convolve with different clean sources to make them sound as if they're in that space. The problem is that this method doesn't really scale well, particularly when we're interested in domestic environments, mostly because this requires an intrusive test signal and we require very low environmental noise to get a high signal-to-noise ratio. Additionally, it requires generally a high-fidelity speaker and microphone to make a good estimate, which is difficult for consumers to get access to. So there's been an increasing interest in this task of blind estimation of the room characteristics, such as the T60 or DRR, which help to characterize aspects of the room that would be useful for doing analysis or potentially creating virtual sound sources. And in that case, we can simply use an unobtrusive test signal, like a speech signal, and then build an algorithm that, given a recording of that speech signal, predicts those characteristics. This tends to be more robust to external noise, and we can use a speech signal as well as consumer-grade microphones. But the problem is that the T60 and the DRR alone, even if their estimation is accurate, does not fully characterize the room, which is a challenge for creating virtual sound sources, essentially. And we would also need to consider things like material properties within the room geometry and others. So there's been a number of deep learning approaches more recently to try to address some of these issues. One approach tries to estimate the parameters of artificial reverberators to match this reverberant speech recording. And while this can work well, it's highly dependent on the quality of that artificial reverberator and whether or not it can match accurately enough the room impulse response of the room in question. So it may not generalize to real rooms, and we are highly dependent on that algorithm. The other side of this is to then use a very much deep learning inspired approach where we have an end-to-end neural network that processes an input signal to match the acoustics of a desired room. The problem, though, is that this requires significant compute not only during training, but also during inference, since a neural network is processing the audio in the time domain. It also has the ability to add potential artifacts, which are generally undesirable for creating high-quality virtual reality experiences. To balance this, we propose an approach that sits in between these two, where we use a deep learning system that estimates the room impulse response directly, which can then later be used to convolve with other input sources to create virtual sound sources within a room. Here's the overview of the architecture, which we title FiNS, Filtered Noise Shaping Network, that reconstructs room impulse responses in the time domain directly from reverberant speech. So this works with a basic encoder-decoder structure, where we analyze a reverberant speech signal to estimate the room impulse response in the time domain. In this case, we use a domain-inspired decoder to do this, where we model the room impulse response as a sum of decaying filtered noise signals along with the direct sound and early reflections. This model operates at 48 kilohertz for high-fidelity audio processing, and we also, in a listening test, show that our proposed method is able to outperform others. So here's a more close-up view of the overall architecture, which I'm going to walk through the different sections now to give you an idea of how it works. But in general, we're analyzing a reverberant signal, and the output of the model will then be the room impulse response from that reverberant signal. So starting with the encoder on the left side, it is basically a convolutional time domain encoder, which uses 1D convolutions. And there's a total of 13 residual blocks, as you can see here on the right side, that are very basic in construction. We use strided convolutions with stride 2 at every layer in order to downsample the signal through the depth of the network, increasing the number of channels through the depth. And at the end, we apply some pooling to generate 128-dimensional embedding at the output. And the idea is that this embedding should then capture relevant information from the input signal about the acoustic characteristics of the room that can then be used by the decoder to reconstruct the room impulse response. In practice, at training, we train our model at 48 kilohertz, and this encoder then achieves a receptive field of about 2.4 seconds, which should be sufficient for capturing the room impulse responses that we're interested in modeling. So moving on to the decoder then takes this latent 128-dimensional embedding to try to upsample it to predict the room impulse response. The design of our decoder is based heavily on the GAN-TTS decoder, which is a speech synthesis model, and it uses these two stage A and stage B blocks, which are just composed of various standard convolution and upsampling operations. We use this film operation, or feature-wise linear modulation, to inject information from the latent, the Z, and a noise vector, N, at every layer within inside the network. And this helps to ensure that the decoder can take full advantage of that information to do the reconstruction. But we also modify this decoder. Instead of directly predicting the signal in the time domain, we restrict it by forcing it to model the room impulse response in two distinct parts. So we take inspiration from room acoustics, where it's common to analyze the impulse response in multiple different parts. For example, the direct sound, then the early reflections, which are about the first 80 milliseconds or so, and then the late reverberation. What we do is then have the decoder model the room impulse response in two different parts. We first have the late reverberation generated with a sum of filtered noise signals, and these filters are learned during training, and the model will then predict time domain masks for each of these noise signals to determine what their decay should be. Instead, for the direct and early components, they are estimated directly in the time domain by the decoder, which corresponds here to the first 50 milliseconds of the impulse response. And this is a much easier task than trying to predict the time domain response of the entire room impulse response. So here's what the filtered noise shaping aspect of the network looks like. So you can see that we have a learnable filter bank, which is just a collection of 1D convolutional filters, FIR filters of about 2,000 TEPs. And we found that actually training these during the process allowed us to get better performance. And what happens is that this part of the decoder then, it gets passed to a sigmoid, so that the decoder is then predicting some sort of time mask in the time domain that generally results in the decaying of these different filtered noise signals over time. And summing them together, along with the direct sound and early reflections that are predicted by the model, we can generate an estimate of the room impulse response. And what we find is that basically this approach allows us to have something of a generative model without having to do any sort of adversarial training for this approach. So to get onto the training aspect in the data generation process, we use a fairly straightforward formulation where we use VCTK to source clean speech, combined with a data set of about 1,000 room impulse responses from our own internal data set. So during training, we randomly sample speech and room impulse responses and convolve them to generate reverberant inputs. These then get passed to our model, which is then tasked with recovering the original room impulse response that was used to create that reverberant speech. In our experience, we also considered two deep learning baselines. In the first case, we consider adapting the wave UNet, which is a popular model for source separation. And in this case, it's a UNet structure in the time domain where the reverberant speech signal is the input and the room impulse response is the output of the model. This model has no inductive bias, so we're curious to see how would it perform compared to our system, where we're trying to estimate the room impulse response. And as with all the models, we train using the multi-resolution STFT. We also consider another baseline, which is to remove this filtered noise shaping aspect from the decoder and instead just predict 48,000 samples directly in the time domain for a 1-second impulse response in the decoder. And what we find is that this is basically conceptually similar to wave UNet, except without the skip connections between the encoder and the decoder. And what we're trying to see here is, does our filtered noise shaping actually aid in the room impulse response estimation? So to evaluate, we report objective results, which are both the reconstruction loss, which is an STFT distance, as well as how accurately the models are able to match the T60 and DRR of the ground truth room impulse responses. And what we find is that all three of these models are capable of estimating room impulse responses that are fairly accurate for both T60 and DRR. We also see that this generalizes to unseen speech not only from VCTK, but also from the ACE dataset, which is a totally different dataset of speech. But interestingly, our listening tests showed that the FiNS-D and the wave UNet baselines produced noticeable ringing artifacts in the generation of those room impulse responses, which we wanted to investigate further that wasn't reflected in these objective metrics. So we we conducted a Mushra listening test with 15 trained listeners. And you can see the results here that the FiNS model outperformed both the WaveUNet and the FiNS-D baselines without filtered noise shaping. And basically our conclusions were that the listeners rated the FiNS model the highest among the different models, but they were still able to differentiate subtly between the room impulse response of the true room and our generated one, but only by a small margin. We also investigated the ability of the encoder to learn interesting information about the reverberant speech. So after passing unseen reverberant speech examples into the encoder, we could then create these 2D UMAP embeddings, and then overlaying here colors for the DRR and the room ID for those different examples. And what we see is that there's a clear structure in this latent space that encodes information about room characteristics that was never explicitly told to the model, which is an interesting result and something we'd like to see from the encoder. So we provide a number of listening examples available on this webpage, and we'll just go through and play a few of them right now to hear some examples. Okay, here we are now at the webpage with the recordings, and first we'll listen to just the original clean speech recording from VCDK with no reverberation.
And I was happy for the happiness of my brothers.
Now we'll hear that recording convolved with a real measured room impulse response.
And I was happy for the happiness of my brothers.
Next, we'll hear the WaveUNet model's prediction of the room impulse response convolved with the original clean speech. And here you'll hear that there's kind of this robotic ringing sound in the decay.
And I was happy for the happiness of my brothers.
And a similar thing for FiNS-D that does not have the noise shaping.
And I was happy for the happiness of my brothers.
And then in FiNS, which is our proposed model, you'll hear that ringing is now gone.
And I was happy for the happiness of my brothers.
It is somewhat subtle to hear in these examples. It's easier to tell by listening to the room impulse response directly. So here's the original room impulse response for that example. And here's what WaveUNet sounds like. FiNS-D. And finally FiNS. So you can hear that there's clearly that we've captured the room impulse response in all of them, but the others, both FiNS-D and WaveUNet, have these clear kind of ringing artifacts. I encourage you to visit the webpage and check out more of the examples if you're interested, but that's all we'll look at for now. Thanks so much for coming to this talk. I hope you found it interesting. Please feel free to reach out if you have any questions whatsoever. I'm more than happy to help. Thanks again and have a nice day.